Welcome to our lecture on exact differential equations. Today we are going to explore a fascinating type of equation that helps us uncover hidden parent functions from their individual changing parts. By the end of this video, you will understand not just how to solve these equations step by step, but what they actually represent in the physical world around us. To understand exact differential equations, imagine you're hiking on a large, uneven mountain. The elevation at any point is given by some hidden mathematical function. If you decide to walk along a perfectly flat trail that wraps around the mountain, your overall change in elevation is exactly zero. An exact differential equation is simply the mathematical version of this flat trail. It describes a scenario where two different changing quantities perfectly balance each other out, meaning the hidden overall function is not changing at all. Now that we have a physical intuition, let us look at the math. Sometimes we encounter a differential equation written with two separate parts added together and set to zero. We call this an exact differential equation if those two parts actually represent the exact pieces of a single hidden parent function. To piece this together, we use partial derivatives, which measure how a function changes when we only change one variable at a time. When we combine these tiny changes, we get the total differential. This brings us to the ultimate test for exactness. How do we know if that hidden parent function actually exists? We use this exactness condition. Conceptually, because the order of partial differentiation does not matter for smooth functions, the cross derivatives must match. The symbol m represents the horizontal change component and n represents the vertical change component. If the partial derivative of m with respect to y perfectly equals the partial derivative of n with respect to x, the equation is exact and we can proceed to solve it. Before we solve an equation, let us visualize what we are looking for. Here is our hidden parent function, represented as a mountain. The flat contour line represents our final solution, where the total change is zero. The arrows show how the m and n components guide us along the surface. By piecing these horizontal and vertical components together, we can reconstruct the entire shape of the mountain. Let us see how this works with a concrete example. Let us solve a basic exact differential equation. We are given an equation and asked to find the hidden parent function. Our first step is always to identify the m and n parts. Here m is 2xy and n is x squared minus 1. Before trying to solve, we must test if the equation is actually exact. We differentiate m with respect to y, treating x as a constant, which gives 2x. Then we differentiate n with respect to x, treating y as a constant, which also gives 2x. Since they match, the equation is officially exact. Now that we know it is exact, we can start building our hidden parent function, f. We do this by integrating the m expression with respect to x. Notice that we add an unknown function g of y instead of a normal constant, because any terms with only y would have disappeared during the initial partial differentiation. Integrating gives us x squared y plus g of y. To find this missing g of y piece, we differentiate our new partial function with respect to y, giving us x squared plus the derivative of g. We are almost there. We know this derivative must perfectly equal the original n expression from our problem. So we set x squared plus the derivative of g equal to x squared minus 1. The x squared terms cancel out beautifully, leaving the derivative of g equal to negative 1. Integrating this with respect to y gives us negative y. Finally, we substitute this back into our partial function and set it equal to a constant, c. This final algebraic relationship represents all the flat contour trails on our mountain. Let us tackle a slightly more complex example involving exponential functions. The logical steps remain exactly the same. We identify m as e to the y plus 2x and n as x e to the y minus 2y. We verify the exactness condition by taking the partial derivative of m with respect to y, which is just e to the y. The partial derivative of n with respect to x is also e to the y. The condition holds true, so we can safely proceed with our integration strategy. We begin building our hidden parent function by integrating the m expression with respect to x, remembering to add our unknown function g of y at the end. Integrating e to the y gives x e to the y, and integrating 2x gives x squared. Now we have the main structure of our hidden function. To find the missing piece, we differentiate this newly built structure with respect to y. The x squared term vanishes and we are left with x e to the y plus the derivative of g. This is the crucial step where we force our built function to match the original equation. We set our result perfectly equal to the original n expression. Subtracting x e to the y from both sides leaves us with a simple expression. The derivative of g equals negative 2y. A clean cancellation like this is a reassuring sign. We integrate negative 2y to get negative y squared. Plugging this back into our main structure and setting it equal to c gives us our final complete algebraic relationship. Now that we have solved these equations, why do we care about them in the real world? They are absolutely essential in physics and engineering, particularly when dealing with energy. A conservative force field, like gravity or an electric field, is described by an exact differential equation. This exactness guarantees that the energy required to move an object depends only on the starting and ending points, not the path taken. Without exactness, you could theoretically generate infinite free energy just by walking in a circle, which breaks the fundamental laws of the universe. Let us summarize what we have learned. An exact differential equation is a special type of equation where two changing parts perfectly represent the total change of a single hidden parent function. By verifying the exactness condition, we ensure this hidden function actually exists. We then use a step-by-step process of integration and differentiation to rebuild it from its pieces. Ultimately, mastering these equations allows us to find stable paths and understand complex systems where fundamental quantities are conserved. You now have a solid foundation in exact differential equations.